Howdy everyone. So this is now the second video based on partial differential equations. I realized that the one I posted before wasn't completed. It only went up to a certain point. So I'm going to redo the entire process from the beginning. And yes, as we were discussing before, this is the video based on the heat equation. Right? So we are trying to solve a partial differential equation for a heat equation problem. So the problem that we're trying to solve goes like this. One end A of an insulated metal bar AB of length 2 meters is kept at 0 degrees Celsius, while the other end B is maintained at 50 degrees Celsius until a steady state of temperature along the bar is achieved. At T equals 0, the end B is suddenly reduced to 0 degrees Celsius and kept at that temperature. Using the heat conduction equation, determine an expression for the temperature at any point in the bar distance x from A at any time t. Alright, so let's draw up the initial condition for our system, and that was before anything happens at point A the temperature is 0, and at point B the temperature is 50, right? And then at T0 the bar is quenched at B to 0 degrees, which will then give you some sort of parabolic curve for the temperature along the bar, right? Okay, so as we've stated before, when dealing with partial differential equations, we start off with general solutions, right? Assumptions on general solutions, and we work through refining those general solutions until we have something that is very specific for our use case. Now, in this case, we take a look at what sort of boundary and initial conditions we've got, right? We know that at the extreme points of the bar, the end points, the temperature is going to be 0 for all time. Okay, so 0 of t is equal to 0, and then u of x of t when x is 2 meters, which is the point B, for whatever time t it will be 0. Okay, so these are boundary conditions. Now we only have one other condition left, and that is the initial condition here before the time starts. Now we know that the temperature at B can be described, the temperature at B is 50 and at A 0, and that gives us this linear line here, and we can describe that with using a linear equation. Okay, so using the linear equation mx plus c, we can describe this line here. Alright, so the first thing we want to do here is to find our gradient, and that is going to be m is equal to y2 minus y1 divided by x2 minus x1. Okay, so that will be 50 minus 0 divided by the length of the bar 2 minus 0, which gives us 25. And so when we input that in here, we've got a linear equation of 25 y is equal to 25x plus c. So now we need to solve for c, right? And we can use any point along this bar. I'll just use the origin point here. So 0 is equal to 25 times 0 plus c, which will mean that c is then equal to 0, and then f of x is equal to 25x. Great. Okay, so let's write down the equation, the heat equation. Du d squared of u over dx squared equal to 1 over c squared du over dt. Okay, and we'll assume a general solution of u being the function of the product of two functions, one in terms of x and one in terms of t. Okay, and so now to represent this in with this symbolism, we're going to just differentiate d of u partially with x and partially with t. So here we'll get x prime times c, and if we do it now for, if we partially differentiate u with t, we're going to get x prime. So we need the second partial derivative now, right? And that's going to be x double prime t. We don't need to get the second partial derivative of this because it's only a first order differential here in the equation. So now we can rewrite this equation as x double prime t is equal to 1 over c squared multiplied by x t prime. And if we separate the variables, bring all the like terms together, then you've got x double prime over x is equal to 1 over c squared t prime over t. Okay, and we know that these expressions are equal to some arbitrary constant which we represent as minus p squared. So if we then isolate these expressions, right, that, then multiply out, okay, and then bring it over. Alright, now the general solutions for these two equations will look like this. A cosine P of x plus B cosine P of x, and then T will take the form C times E to the negative P squared C squared of T. Alright, which then means we've got a general solution that looks like this for our heat equation. Okay. And that is multiplied by C e to the minus P squared C squared T. Alright, so now let's just neaten it up a bit. We can distribute this constant here into the bracket and have some new arbitrary constant P being the product of A and C, and some new arbitrary constant Q being the product of B and C. And we're also going to now introduce an eigenvalue. So we'll say PC is equal to lambda, which then means P is equal to lambda over C. Okay, so I'm pretty sure the reason why, I still don't know, I'm pretty sure the reason why we introduce lambda is because we're evaluating, you'll see later, these expressions for multiple iterations, and that bleeds into Fourier. Okay, let's carry on. So our now refined equation. So we're working at the start with a general solution, but we're trying to get a particular solution for our specific use case. So it's not A anymore, it's Q now. Okay, it's P. Alright, so yeah, substitute this now in for P. So it's lambda over C times X plus Q sine lambda over C X. Okay, and then you've got e to the minus lambda squared T, right? Because up here we've got this P squared, C squared, which is effectively just squaring all of that. Cool. Past midnight. Alright, so now we're going to start refining our equation using the boundary and initial conditions that we've got up here. And the very first one we're going to use is this one here, u of x of t, where x is equal to 0. Okay, and so 0 then equals to p cosine. If we substitute 0 for x, that whole part becomes 0 plus q sine, same for this part here, and that's all multiplied by e to the minus lambda squared t. Okay, and so cosine of 0 is 1, sine of 0 is 0, so that will reduce just to these two things here. And so now we might ask ourselves, what is the most reasonable value we can make here equal to 0 in order to make this expression true? And we certainly don't want that to be e of negative lambda squared t, right? Because t can't be, because the t is going to be useful to us in expressing this equation. So that means p will then have to be 0. So now that we've got our value for p, we can then substitute that into the most recently refined solution that we've got, which is this one here. Okay, so substituting p equals 0 up here now will give us the refined solution of q sine lambda over c x e to the negative lambda squared t. Cool. Now we're going to use the next boundary condition. U of x of t, where x is equal to 2. I'll just continue as we did before. So here 0 is equal to q of sine. Now substitute 2 into x, so we'll have 2 lambda over c multiplied by e to the minus lambda squared t. Okay. Now we ask ourselves again, which term here is best to be made equal to 0, and it certainly now cannot be this constant q, because if q is 0, then this whole expression becomes 0, and that will be useless to us, so we can't do that. We don't want to make this 0 again, so the only thing left is sine 2 lambda over c. Alright, so again, this one we don't want being 0 because t does become a variable at some point, so we'd rather keep it within the expression, whereas these two are constants, but q technically this isn't a constant, because lambda will change the value of this expression, but q can never change at all, so that's why it cannot be 0. So sine 2 of lambda over c is equal to 0. Now our interest is going to lie in this here, which is our angle for this trigonomic function 2 lambda over c, which can be seen as n pi, because when evaluating trigonometric functions in radians, all of the angles you input, or the values you input in there, are just factors of pi, and this n here just represents the scaling value for pi. Okay, so now we can solve for lambda, okay, which then becomes n pi c over 2. Cool. Yeah, so now we can leave this. We can leave this as is, but before we move on, we need to consider the fact that because we're working with n, and n becomes values from 1 up to infinity, right? We need to now further refine this equation to represent the summation of all of those different iterations of n. So you'll see, I'll take you to the actual notes here and just show you what that looks like. So for your eigenvalues here, where n is your variable, which increments up until some arbitrary number r, you'll have your corresponding eigenfunction, and then that can be expressed as this infinite summation down here. All right, as you add each eigenfunction. Okay, so u of x of t now is equal to the infinite summation as r from r equal to 1 for q of r sine of 2 lambda r over c e to the minus lambda r squared t. Okay, so now to finish up this process, we're going to evaluate what this constant qr is, and so to do that we use the Fourier series method, and that is 2 over the period from 0 up to that period of f of x sine n pi x over t in terms of x. Okay, so remember what f of x is, right? We got that up here. It's 25x. So now this is us using the initial condition to further refine our solution. Okay, so let's input everything 2 over 2 from 0 to 2, 25x sine n becomes r pi of x over t d of x, sorry. Okay, so that will cancel out, and we can take out 25 since it's a constant. We don't need it for the integration. 0 to 2 x sine r pi of x over t d of x. Okay, so we're going to use integration by parts to solve this. uv minus integration of v du, okay, where u is equal to x, therefore du is equal to d of x, and dv is equal to sine r pi x over t. It's no longer t anymore. I was supposed to put the actual value of the period over 2, and right here over 2. So v then is equal to negative 2 over r pi cosine r pi x over 2. Sweet. Now let's input that into our equation. Say we got 25 multiplied by u times minus 2 over r pi cosine r pi x over 2, right? And this is technically evaluated from 0 to 2, but we don't have to consider that right now. So I'm going to add a plus here because this negative is just going to be drawn out of this integration. So it's 2 over r pi multiplied by the integration from 0 to 2 for cosine r pi of x over 2 times this d of x here. Okay. So I'm just going to drop this, we don't need it right now. So minus 2x over r pi cosine r pi x over 2. I'm also going to drop this, also don't need that right now. Plus 2 over r pi multiplied by, this integrates to 2 over r pi sine r pi x over 2, and that is from 0 to 2. Alright, so we can just go ahead and just fold this in, just evaluate that. So we're left with 4 over r squared pi squared. Cool. Now we can evaluate this between the limits. So the first one will be 2 times 2 over r pi multiplied by cosine r pi multiplied by 2 over 2 plus 4 over r squared pi squared sine r pi 2 over 2, and then that's going to get subtracted by the lower limit, minus 2 times 0 over r pi cosine r pi 0 over 2 plus 4 over r pi squared sine r pi multiplied by 0 over 2. Okay. Yeah, so this term we'll just evaluate to 0 because sine of 0 is 0. This term will evaluate to 0 because this is 0 here. and this term here will also evaluate to 0 because sine of any integer is just 0. So this will cancel out, and r can only be integer values. So that will just fall away as well. So what we'll be left with is this 25 that we have there multiplied by minus 4 over r pi cosine r pi. No, okay, well let's cancel out. So it's just r pi. Cool. So we can simplify that to minus 100 over r pi cosine r pi. Cool. Now this can be rewritten to further simplify it. Cosine of r pi can only be two values depending on the value of r. If it's odd, then it'll be equal to -1. If it's even, it'll be equal to +1. That can be expressed as -1 to the r. Okay, and so this negative can also be factorized from the 100 here. So you'll have 100 over r pi multiplied by -1 times -1 to the r. That'll give you 100 over r pi times -1 r plus 1. Okay, and that is our constant q of r. So now we can input our constant back into the the latest refined form of our particular solution, which is up here. Okay, in fact I'll just copy this. Okay, just paste it here. Cool. So this, let's move to the next space. Alright. So this in effect is our final solution. Only thing that you should do here is just express again what lambda equals to, and that is 2 pi c, not 2, is, it's divided by 2, but is multiplied by r. Yeah, and r is any positive integer value. Okay, so that's it. If you take a look at the answer here, that's exactly what you're seeing. The only difference is that they just factorize this. They bring out this 100 over pi as a constant and leave in the 1 over r. But you would definitely see that yeah, -1, r plus 1. And this pi x. Yeah. So before I forget, this 2 here needs to become x again, because it was 2 before when we were evaluating for one of our bound conditions. Yes. So now everything is as it should be. Alright.